So we've done a lot of talking about quadratic equations and quadratic functions in the last chapter, chapter 4. Now we're going to be moving on to chapter 5, and the first topic is solving quadratic equations. So I want us to stop for a minute and think about what we already know about what it means to solve an equation, just any equation in general. So for example, if I gave you the equation let's say 2x plus 3 equals 7. And I said, solve this for me. Well, what would that mean? What would it mean to solve it? Well, I'm hoping what you're thinking about is that if I'm solving this, what I'm doing is I'm finding out the value of x. In other words, I'm finding the value of this variable and that is unknown. So, that's what it means to solve an equation, is that you find the value of the variable. And sometimes there is more than one variable, so I'm actually going to make this plural, right? We saw in our systems of equations where we had x and y that we needed to solve for. And so in each type of situation where we're solving, there may be the meaning of that variable. In other words, what does that variable really mean? And so today what we're going to talk about is how to solve quadratic equations, and also what it means and what we've found when we've solved for the variable in a quadratic equation. So it turns out that when you actually solve for the variable in a quadratic equation, that solution represents the x-intercepts, or as we've been calling them, the roots. They're also sometimes referred to as zeros. So in other words, in this function here, y equals 1/2 x squared plus 2x minus 3, when I solve for x, then what I'm solving for are the roots. That's it. So let me explain a little bit more about how that works. So I've just opened up the page so that we can see a parabola here. You'll remember that from grade 9 math, that to find the x-intercept, the value of y is 0. So in other words, where the graph crosses the x-axis, whatever that may be, whether it's a line or a curve, we say that the x-intercept is located where it's crossing the x-axis, and that also the value of y has to be 0. So that I know that if I highlight, this little spot here and this little spot there, those I know from previous experience are the roots of the quadratic function, and they're also the x-intercepts. So what I can go ahead and do is say, well, where are these values? When the y value is 0, what is the value of x? And so I can clearly see that from the graph. If I count over, I can see -1, -2, -3. So I know the solutions here are going to be x equals -3, and it looks like x equals 1. And so in that case, that is the solution to this equation. That's what I found is the roots. So now how are we going to go about that? Well, that's going to be coming, how can I find the solution to this without necessarily graphing it? And that's what I'm hoping we'll get to in today's lesson. Before we move on to the mechanics of how to solve, I think it's important for us to know what to anticipate with our answers. So I want to open you up to 3 different possibilities. Let's start with the simplest, which is that we have 2 distinct roots. So for example, that would be the case where I have a parabola that is maybe opening upward like so, possibly opening downward like so. But in either case, I have 2 distinct roots. And I can see that, I can see that right here, and right here, and likewise right here and right here. So in each of these parabolas, I have 2 distinct roots. What I want you to think about next is, well, what are some other possibilities? What are some other situations that could happen? Where could these parabolas be situated? So what I'm hoping that you thought about was that one possibility would be that the parabola's vertex is actually sitting on the x-axis, right? Whether opening upward or downward. So what would we say there? Would we say it has one root? Well, we would say that it actually has two identical roots. And you're going to see what that looks like when we look for our solution. So we would say it has two identical roots. Now there's a third possibility, so take a minute to think about what that might look like. What I'm hoping that you're thinking about is the fact that I could have a parabola that has no roots, that doesn't cross the x-axis at any point. We've seen that with our translated parabolas, that they can end up in positions where there are no roots. So what we're going to look at is we're going to look at a situation where at different situations where we solve for the roots, and there may be the situation where we have two distinct roots, and your answer will tell you that. You might have a situation where you have two identical roots, and based on what your solution looks like, you'll be able to identify that. And same with there being no real roots. All right, so now I think we're ready to get into this. So how do we go about solving quadratic equations? Well, we have to use factoring as a method. And so if at this point you need to stop the video, go back and revisit how to factor, that's going to be an important prerequisite, which is why it was emphasized earlier on in the course. So let's move on to how factoring will help us in this. So here's a question just to get us thinking about why what we're about to do actually works. If I posed you the equation a times b equals 0, what do we know must be true for either a or b, or even both of them? Well, what I'm hoping that you thought about was that either A has to be 0 or B has to be 0, because the only way that I have two factors that multiply to give me 0 is if one of the factors themselves are 0. So we're going to apply that when we factor. So you'll remember, I'm just going to make up an example here. You'll remember in our factoring section that we would have ended up with something that looked sort of like this. I'm going to say y equals x plus 2 perhaps, and maybe x minus 3, right? And so you'll also remember that what we did when we were looking at our parabola was we said, well, the solution is where we have our x-intercepts. In other words, the position where y is equal to 0. So I have to go therefore and say, okay, well 0 therefore has to be equal to x plus 2 times x minus 3. Well, same as with a times b equals 0, where one of either a or b has to be 0. In the same situation where I have a factored form of the quadratic function, I know that either x plus 2 has to be 0 or x minus 3 has to be 0. One of them has to be 0 in order for my left side to be 0. So that's how we're going to go about solving our quadratic equations. So what is the moral of this story? If a quadratic equation is factorable, then it can be easily solved. And that's how we're going to go about solving our quadratic equations today. So as always, I like to break this down into steps. And I think that the steps will help this to be, you can just kind of go at it at your own pace, and it helps to break it down. So in this case, what I haven't done and I should have done is this should read y equals x squared plus 9x plus 14. So the steps that you want to take are to bring all of the terms to one side of the equation and let the other side equal 0. Now this is the case if there is no 0 anywhere, and you have a y there, then all that you need to do is simply to replace that y by a 0. So, you'll see what I mean because we'll look at some examples that will show that. So in this case, all of my other terms were already on their own side, and so they stayed exactly where they were. So there, I've accomplished step 1. Step number 2, factor completely. So remember to factor completely. You might want to revisit that factoring flow chart that I provided you with earlier in the unit. You'll remember that you always want to remove the common factor first, and then proceed to factor a trinomial, or we could even have a difference of squares by whatever method is appropriate. So in this case, I see that there doesn't appear to be a common factor, and I can also tell that this is a simple trinomial because the coefficient of the squared term is 1. So this is the type of question where what I want to do is I want to say to myself, well, I need two numbers that are going to multiply to give me 14, but they're going to add to give me that middle term, which in this case is 9. So I need to think about, well, what are those values? So I tried to start off with a question where the factoring was not really a big stumbling block. And so hopefully you were able to come up with 2 and 7. 2 and 7 multiply to give me 14, but also add to give me 9. And so that creates my factors. So I'll have 0 is equal to x plus 2 and x plus 7. So there I have it in factored form. And so you'll remember that in the last little snippet of our conversation, I talked about how one of these factors, either this guy or that guy, has to be equal to 0, right? In order for the left side to be 0. So that's what we need to do in the next step. We need to set each factor to 0 and then solve for x. So I'm going to say I'm going to set this guy to 0 and I'm going to set this guy to 0. Now normally we want to do that stepwise, and in this case the solution's fairly easy. So I would say, well, either x plus 2 has to be 0 or x plus 7 has to be 0. In which case x is either -2, x is and x is -7. So this is giving me some information. This is telling me that my roots are going to be positioned at x equals -2 and x equals -7. So there, I've solved this quadratic equation. Let's try some other examples. All in all, though, this is the basic process you're going to go through. You're going to bring all your terms to one side, factor. Now, factoring can be the stumbling block because we know there are many types of factoring. But then once it's factored, you're simply setting each of the factors to 0 and then solving for your variable. So I'm hoping to show you a bunch of different examples about different scenarios, but ultimately you're going to have to do the practice to really get a true sense of the types of questions that are out there. So in this question it will say solve for x or solve the quadratic equation. Notice that there's a couple things I noticed right away. First of all, that the equal 0 is already all on its own on one side, and that was our first step, and so that we can check off. The next thing I want to do is I want to factor it completely. So factoring completely means I'm going to first look to see if there is a common factor, and I can see that in each of these there is an x that is there as a common factor. So I'm going to pull out the x and write x, and then what's left? 2x plus 5 equals 0. And so now I have factored it. There's nothing else that I can do to factor it. And I know that either x is equal to 0 or 2x plus 5 has to be equal 0. It's the only way that this whole thing will equal 0. So now what I'm going to do is I'm just going to set each of the factors to 0. Either this is 0 or this is 0. So my two roots are x equals 0. And I can find the other one by saying 2x plus 5 equals 0. So 2x equals negative 5. So x is equal to negative 5/2. And your textbook may or may not leave that as a fraction. It may also just write it as negative 2.5. So there's my solution. I've solved by finding that the roots are at x equals 0 and x equals negative 2.5. All right, let's look at a second example here. So 6x squared minus x is equal to 15. So you'll remember that the first step that we took was to move everything to one side, all the terms to one side, and equate the other side to 0. So that means that I'm going to bring this 15 over and leave the 0 on the right-hand side. That's going to leave me with 6x squared minus x minus 15. So now I'm going to carefully examine this to decide how I'm going to go about factoring it. So I can see that, first of all, there is no common factor to be removed. I do notice that what I have is a trinomial. There are 3 terms there. But the coefficient of my squared term is not 1. So that means that this is a complex trinomial. And so I can factor this either by using the decomposition method or by using my quicker method that I taught you. Whichever you want to do is fine, but I'm going to remind you of a few details here. So you'll be reminded that I need to find 2 numbers that multiply to give me the product of my first and last term. So in this case, 6 times 15 is going to give me 90, negative 90, I believe. And then I'm looking for 2 numbers that are going to add to give me negative 1. And so you can take a minute, pause the video, and think about that and try to factor this. Otherwise, you can follow along. So I'm thinking about all of the factors that multiply to give me 90, and the fact that I have this negative 1 here tells me that the numbers that I'm looking for are only 1 apart from each other. So I can tell immediately that those numbers are going to be 9 and 10. And since my 1 is negative, the larger value of 10 is going to be the negative value in my factor. So there I go. So now I'm going to use my quick method, and I'm going to remind you of the details. So I'm going to take it a little bit more slowly just in case. So I'm going to take those 2 factors, 9 and negative 10, and I always want to divide them by the coefficient of my squared term, which in this case is 6. And then I go ahead and I reduce that fraction. And so 9 over 6 is the same as 3 over 2, and negative 10 over 6 is the same as negative 5 over 3. So that will enable me to create these factors. So I'm going to have my 2 brackets equals 0. My 1 factor, this 2 here, becomes the coefficient of my x, so 2x. And since it's positive 3, I'm going to say plus 3. Now I'm going to do the same over here. So the 3 as my denominator tells me that the coefficient of x is 3, and that this minus 5 on top means that I need to say minus 5 as my factor. So now I feel like the hard part of this question is done. And all I need to do at this point is remind myself that, okay, well now I'm just going to set each of these brackets to 0 and then solve. And I think you're going to find something interesting here. So I know that either 2x plus 3 is equal to 0 or 3x minus 5 is equal to 0. I'm going to go ahead and solve this. So I know that this first equation, this first root the equation is going to look like 2x equals negative 3. So x is equal to negative 3/2. And then I'm going to do the same thing with this second factor. 3x is equal to 5. So x is equal to 5/3. So I'm hoping you noticed that the factors that we had over here when we began look a lot like the roots that we end up with in the end, except for their sign. So that is one way that you can also quickly solve the quadratic or know what the roots are going to be. All right, so that was a harder example, mostly because of the factoring. But let's move on to another example. So I want you to take a close look at this third example and try to identify what type of factoring it is that we might have to do here. So I'm gonna see it. Let's see if you're right. So what I see when I look at this is that my first term is squared, and that my last term is a perfect square. So I have perfect square, separated by a negative sign. I also notice that I only have two terms in this equation. And so what that tells me is that, combined with the fact that I have a perfect square, and I have a difference, that this is in fact a difference of squares. And so factoring this ends up being fairly straightforward. So all the terms have been moved over to one side, leaving a 0 on the right hand side. When you factor a difference of squared, you always have two brackets, and one of them ends up being a plus, and the other one ends up being a minus. And so when I go ahead and what do I have to do next? I take the square root of the first term, which happens to be x, and the square root of the last term, which happens to be 5, and put each of those in the brackets. Let me write that a little bit more neatly. So x plus 5 times x minus 5 equals 0. And so there I am. There's my difference of squares. So now I'm going to go ahead and set each of these brackets to 0. And so x plus 5 equals 0. So one of my roots is that x is equal to negative 5. The other is x minus 5 equals 0. So x is equal to 5. So there I have my two roots. So in all of the examples that we've seen so far, what we have seen is a case where I have two distinct roots. So in other words, I know that I'm going to have 2 points that I'm going to be able to plot, and that is, so for example, here I have one at negative 5 and here another one at positive 5, just doing a really quick sketch here. And so those are two distinct roots. And so it's not always going to be that case. So let's look at a couple of examples where it isn't in fact the case. All right, so I'd like you to take a minute and try out this example. I sort of have added it in, so I apologize that it's not typed out, but I'd like you to give it a try and see how it goes. Okay, I'm going to take up this question now. I'm first seeing that I have this negative 9 on the left-hand side, and I'm going to move it over so that I end up having x squared plus 6x plus 9 on the right-hand side, and then that leaves that 0 on the left-hand side that I need. Now I'm going to go ahead, I'm going to factor this. Now some of you may have noticed that this is a perfect square trinomial, but in case you didn't, I see that this is a simple trinomial, so I know I'm looking for two numbers that are going to multiply to give me 9 and are going to add to give me 6. And I can see right off the bat that those values are 3 and 3. And so factoring that means that what I end up with is x plus 3 times x plus 3, right? So I can see here that I have as my solutions, setting each of these factors to 0, that I have both roots at x equals negative 3. So these are what we call two identical roots. And so in this case, if I were to graph this, what I would expect to see at negative 3 would be a graph that is kissing the x-axis, but not really crossing it per se, giving me two identical roots. So if you have a situation where the roots that you get give you the same value, that really means, that translates to a parabola that is simply touching the x-axis in some way. Now you may be wondering, well, how does she know that it opens up? Well, we can't forget some of the lessons that we've learned in other previous parts of this chapter, which is that I can see that the coefficient of x squared is 1, and that is really just my a value, so a is equal to 1. So that means that this is, because a is a positive value, it's opening upward and also has not been stretched. So it was fair for me to go ahead and draw that as upward facing. Let's look at one last example. Okay, so since I added in an extra example, this will be E. And so when I look at this, I can see that, first of all, it already has one side equated to 0. So all that I need to do is I need to look at the left-hand side and see how I can factor it. So at first glance, this may look like a difference of squares, but remember, in order for it to be a difference of squares, I would be expecting to see a subtraction between these two terms. So even though I can see that the first term is a perfect square, the last one is a perfect square, in fact, this is a polynomial that cannot be factored. So I would say that this is not factorable. So not factorable means that there are no real roots. So this is one of those parabolas that has no real roots. So presumably it's going to be sort of somewhere up in this sort of region, not ever crossing my x-axis anywhere. So if you stumble upon a quadratic equation where you cannot factor it, that doesn't always necessarily mean that there will be no real roots, but certainly you can't find the factors easily. And so for now, it's okay. We're going to that's what we're going to put for now, no roots. So I want to be clear here that just because it's not factorable doesn't always mean that it doesn't have real roots. It just means that those roots are not really nice, pretty numbers. I want to approach solving this from a not factoring point of view, just to show you that I know that in this case there aren't going to be any real roots. I'm going to go back to maybe some grade 9 math before we knew anything about factoring. So if I said to you, solve this, but without factoring, what you might do is you might say, okay, I'm going to move that 25 to the other side of the equation and make it negative. And then now I need to get rid of that square. So how do I eliminate a square? Well, I do the opposite operation and I take the square root. Right? Well, in so doing, I end up with x being equal to the square root of negative 25. And we know that that happens to be undefined. Go ahead, if you don't believe me, type it into your calculator. We can't find the square root of a negative number because there aren't two of the same numbers that can multiply to give me negative 25. So there we have it. There's another way that we can see that this, in fact, has no real roots because the value that we get for x happens to be undefined. So I know that was a long video. I meant to provide you with as many examples as possible so that you wouldn't be struggling through your homework today. We're going to revisit some word problems tomorrow and give you some examples to practice tomorrow, so stay tuned for that.